Okay, so now we got control over stationarity and invertibility. And I mentioned this a couple of times before, but just you can say you can have it as we've done for the ARMA models, univariate models as well. You can have it as operators with B, or you can have it where you kind of spell it all out with all the coefficient matrices that you need. Depending on which kind of calculations you're doing, you may prefer one or the other. So you can say over here, what I wiped out over there, well, if you want to do the set transform, it's often nice to have it as an operator polynomials, but what we get to now, looking at correlation structures, it's nicer to actually have yt minus 1, and so forth, just as we did when we did it for the ordinary univariate series. Now, the auto-covariance matrix function. We actually did this last week, to some extent. Same. What did we do? We looked at cross-correlation between two different series, right? Now, if you consider it as a multivariate system and do the cross-correlation between x and y, what do you get? You get the off-diagonal part. That's where you got the information about the off-diagonal part last week, right? You have the correlation, autocorrelation structure of the initials. That what kind of gives you information about the diagonal. And then when you look at the off-diagonal, that's where you get the cross-correlation. So if we just look at a bivariate case, then we have the auto-covariance in the diagonal, and the off-diagonal, you have, you can say, the covariance between between state 1 and state 2, and state 2 and state 1. Now, the somewhat mind-boggling part is that that's actually equivalent to, say, gamma 2,1 is the same as gamma 1,2 of minus k. That's one of the small mind-boggling things that you just have to look through. I will just say it in words right now. If you have series 1 and you look at how does that depend on previous values of the other series, that's the same as looking at how is the, say, I'll go 3 steps backwards in time. That's the same as going the other way, looking at from this state to the other state and go 3 steps forward in time. Right? Does that make sense? So that means gamma 2,1 of k is, if you revert the time, then you revert the order down here. You go from one to the other, or from the other to the first one. Then you revert time. And thereby you go from k to minus k. I hope that is intuitively fairly clear. But what does that also mean? If I look at this here, I want to prove the relation up there. So if I do take gamma of k here, and I want to calculate the inverse of this. No, sorry, I want to calculate of minus k. That's what I want to do. With the same example as up here, what I get is, now I'll just write it out, gamma 1,1 of minus k, gamma, 1,2 of minus k, gamma, and I will use this notation over here, gamma 1,2 of minus minus k then becomes just k. And then I have gamma 2, 2 of minus k. Now, when I look at this, there are two minuses that I can just remove. Which two? Yes? The ones in diagonal, because if you look at the correlation or covariance with yourself, going forward in time or going backward in time, k step is the same because it's with yourself. If you look at how do you predict, how do you depend on 3 steps in the future, or you stand here and how do you depend on 3 steps in the back? Since you're doing it with yourself, it's the same thing. So this is gamma 1, 1 of k, gamma 1, 1 of minus k, gamma 1, 2 of k, and gamma 2, 2 of k. And if you look at this, it is the transpose of this matrix here. So this is the transpose of uppercase gamma of k. And then the only difference to that expression up there is that up here the transpose is not there, but here. So if I transpose everything, it will of course also hold. So whenever you go backward in time for the multivariate autocovariance function, then you do not just go backward in time, you also have to transpose relative to going forward in time. So that's one important thing to keep in mind. Now, how do we plot this? What we did last week was to actually do exactly plot this matrix, right? You look at the autocovariance or correlation structures in the diagonal, and then you have the forward and backwards in time in the off-diagonal elements for the cross correlation. That's what, if you just do ACF of a matrix, well, I mean a bivariate time series, then you get a 2 by 2 plot, as we looked at last week. But you can also do what we also did last week, to plot the cross covariance function, where you just plot gamma 1, 2 forward and backward in time. Whenever I did the simulation example, I started doing that first, and then later on I did it for both x and y and looked in lags -3 and -4. That was where I got the information. So last week I did both of these. I think for practical purposes, when you have, in particular, if you have higher order systems than just a bivariate system, then what you want to do is to look at the matrix of parts of the autocorrelation and cross-correlation parts, as is the default of ACF. I think that's the easiest thing to work with, where you make sure that you get all combinations included. Because if you have a three-dimensional system, then you have a 3 by 3 matrix here. That's easy. But if you want to do it the other way, well, it's easy to do all the correlation functions with yourself. There are 3 of those. But how many cross correlations do you need to calculate? Sorry?
M choose 2, where M is the number of variables.
M?
Choose 2, but choose 2 from.
Okay, choose 2, yes. Yes, yes, so in this case you'd have 3, where you go both forward and backwards in time. But presenting all this, when you get to a higher dimensional system, all of a sudden keeping track of where you are becomes quite difficult. I can say that by experience. Whereas the matrix structure here works as long as you can display it in one plot. There's also a border there. If you have a 10-dimensional system, having 10 by 10 plots, it's probably too much for most screens and eyes in combination. But that's another. So now what we did for the univariate systems was to start out saying what are the theoretical expressions, and then we get on to how to estimate things. So if we have these matrix coefficients here, and we have the covariance structure of the noise, then what we can do in case of a pure autoregressive model, then we can do a multivariate version of the so-called Joule-Walker equations. I'll show that in a moment. And in the case of a pure moving average model, then you can also do a multivariate version of what we did previously for the moving average univariate models. And if you have a combination as a multivariate autoregressive moving average model, well, then you go again and pretty much you just say everything that was just a number before now becomes a coefficient matrix. And if you keep track of what should be transposed and what not, you can walk through it. It is effectively just the same. Now, to give one such example, the multivariate AR model is often named a vector, or actually generally all these multivariate armor models, they are sometimes referred to as vector armor models. So using a V there instead of an M for multivariate. Same, just different. It's one of those cases where literature is, I don't know how many times have you seen the same thing defined with different names in two different contexts. But mathematically, it's the same. I mean, I expect that you will all see it at some point in time during your career. A few of you already done it, but in order not to confuse you too much, I'll just say that you have those two options. Those are the general formulations. So we have this general formulation where you just have a phi polynomial on the left-hand side, or we can do where we move everything but yt. Remember, it's a vector. We move everything else to the right-hand side. Now, in order to calculate covariances, what do? We multiply with itself, and then we do some expectations. Now, what I've done here is that I took yt and then I post-multiplied by the transpose of what is up there. So when I post-multiply by the transpose of this, I've swapped the order. So that is saying that's the autocovariance at lag 0. This is at lag -1 and down to lag -p plus sigma. Now, that's one equation, but I have p coefficients that I want to estimate. So I need more than one equation. So what I do now is that, first one step, instead of doing it where I post-multiply by the transpose of where I insert this, I could have taken this up here and post-multiply by yt. If you walk through that, you will see that what you get is you transpose each of these terms here. Because you transpose your starting point, you will also transpose your ending point. And by the way, since the autocovariance so the covariance actually it is because we are at lag 0. What holds for that? it's symmetric. So that means that doing the transpose gamma 0 is of course also gamma 0. Therefore, it should also hold out here. The only thing that I do not need to transpose is sigma, because that is already a square matrix that is symmetric. So whenever I do calculations further down, I can pick and choose between those two formulations. That's the core of this. Now, if I go to gamma 1, or generically gamma k, what do I get? Well, then I do the same thing as I did up here. Then I look at all these equations here, and what I see is I have to look at what is the time difference in all of these. The first one is easy, gamma of k. Then I have gamma of k minus 1 on phi 1 down to gamma of k minus p. That's the time difference, times phi of pt. Now, that I can do for any k. Then what I have to look at is, when I organize things, I take all these equations, all these k equations, to estimate k coefficients. So in an ARP model, I will use k. You go to p order here. Now, what you will see is that you will go forward and backward in time. So you're going to be using this expression here. Therefore, you have it here, and then you have it transposed up there. That's what you will see when you look at what is happening to these numbers. Up here, we have negative indices everywhere. You will have, when k is 2 and p is, say, 4, that will be negative as well. But you will, when you go through it, you will see that you need to have some of those you need to go from a positive to a negative element here. So here, everything is done to get positive coefficients, which means I have to use this version here, where now I say it wrong. Next one, I have this one here. Gamma of 1 transpose is equal to gamma of minus 1 not transposed. So, yeah, it's correct. I just have to say it right. Gamma of 1 transpose, as I have it right there, is equal to gamma of minus 1. And that's what I have here. But here I have it so that all these arguments in here are positive, because k is the maximum order that I'm going to. So down here, when I look at these here, these will be positive and positive, but again, it depends on the numerical value of k and p. So that's why when I'm above the diagonal, I get the transpose in order to change the sign of the argument in here. Okay? Maybe that's one thing to go back home and just do the mental math there and transpose what you have to transpose. Take an vector autoregressive model of order 3 and write it up, because then it's only a 3 by 3 matrix that you have to look at. It's only half a page. So, one thing that you kind of have to just note to yourself is that if you take any armor model, also any vector armor model, you can rewrite it as a multivariate vector autoregressive model of order 1. What happens is that you just increase the order of your first order model. And this is, by the way, I don't know if you've done that, but if you look at differential equations, if you look at a second order differential equation in continuous time, and then you can write it as a first order differential equation of dimension 2. Have you all done that? That's the exact same thing that happens here. Just in discrete time, but the difference equation is the same story. You can take a second order difference equation and write it as a bivariate first order difference equation. That is what is happening here. The hard part is to go through the moving average part and actually verify that this model structure here is equivalent to that model structure there. So what is the dimension of this system? Well, if you have a pure, let's say you have a bivariate model. Let's assume that the ARMA model up there is bivariate, and you have an, let's say that we take an ARMA 2,3 model. Then P is equal to 2. So I need to have at least, and each of these matrices are 2 by 2 matrices. So my bound here is to say that I need at least 4 rows in this matrix, right? But now, in this case, the system is dominated by this over here. So I want to have theta 3 to be non-zero. That actually means if I want to have theta 3, then I need to use a p up to the 4th order to represent the model. So I will, in that case, need an 8-dimensional VR1 model to represent a bivariate ARMA 2,3 model. So what happens in there? The extra phi elements that I have to add here, they will of course be 0. So what happens is that set P represents epsilon on the very old, epsilon t here on theta p minus 1. Now what happens to the next level? When you go one step up here, then you have a diagonal. So you take what was in the last state before, and then you add something. Maybe I should actually walk through this and show you how it works. Did not put it into my notes, but anyways, let's not take a complicated model to start with. Let's take a model where we can actually see what happens and do that. So let's take a moving average model of order 2 and see what happens here. Then what we have, let's just do it univariate, because to do it multivariate is again, it's a trivial thing where you just say that every coefficient here is a matrix instead of a number. So we can do it a univariate. It gives you the same thing. So what should we do? Again, we should look into how to define the model order. We have no AR part, so we need to go over here to figure out what should the model be. So we have something on epsilon t here. We have a 1, we have a theta 1, and a theta 2. That's what we have. Then we have a plus. Now we kind of define the dimension of the system. Set 1, comma t minus 1. Set 2, comma t minus 1. And set 3, comma t minus 1. And then what we have on the left-hand side is set 1, comma t, set 2, comma t, and set 3, comma t. And the coefficients in here, well, since we don't have an AR part, the first column here are just 3 zeros. And then what we have here, we have a bottom row of zeros, and then we have an identity matrix that fills the rest of this. So I have a 1 there, and a 1 there, and zeros outside the diagonal. That is what is meant by what is written up there. Okay, so let's make this the model. And what we care about is what we call yt up here. That corresponds in the end to set 1. But if we look at this model here and try to walk through it, what is actually represented where? So let's take it at one time step, take it from the bottom and do it bottom up. So set 3, comma t, that is equal to a lot of zeros, theta 2 epsilon t. Right? Now if we go for set 2, comma t, what is that? That is 1 times the previous set 3 as set t minus 1. So what is that? Let me just write it out. So that's set 3, comma t minus 1 plus theta 1 epsilon t. Now this here, set 3, comma t minus 1, well, we can get that from up here. We just have to shift time. So this is equal to, and I'll take, just to do to get back to what the usual order of elements, I will write theta 1 epsilon t first, plus theta 2, and then I have to shift time. So I get epsilon t minus 1 there, right? And then I have to go back. What is remaining is set 1, comma t. Well, set 1, comma t is the previous set 2, comma t. So that's set 2, comma t minus 1 plus just epsilon t. And now again I will swap the order of elements just to get it the same order we usually have it. So we get epsilon t plus, and now set 2 at t minus 1. Well, we just did it at time t. So we just have to take this up here and shift time backwards 1 lag, right? So I take the coefficient theta 1, and then I have to take, that becomes epsilon t minus 1, and then I have plus theta 2 epsilon t minus 2. Hey, we're done. This is just an MA2 model wrapped in a very nasty matrix form. We can do the same thing for a pure AR model. That's also fairly straightforward. The challenge becomes to see, the recipe is the same. You just start from the bottom and see what comes in everywhere. And then what you look at when you do it for an armor model, a general armor model, it's a little bit more tedious to see how everything are related, but it's the same thing that happens. I would say that's a good exercise to do it just for an AR model. Maybe I should just post hoc write that this is exactly YT, as we wanted it to be. So, identification We need to identify what we're looking at before we can estimate parameters next week. We look at the auto-covariance matrix functions. Now, or I tend to always use the correlation function instead because it's normed, but that's just because when we do that, this is about being near zero. We have the usual interpretation of what is the variance of that. That is, if it is a white noise signal, then the variance of the correlation to some given lag, autocorrelation to some lag, or cross-correlation to some lag, if it's white noise, is the square root of n. The variance is 1 over n, sorry. And thereby what we look at is plus minus 2 times the square root of n, 2 over the square root of n. That's the 95% confidence interval that is drawn whenever we look at the autocorrelation function. So we have pretty much the same thing here as we did for the univariate model, the so-called golden ARIMA table, or ARMA table. So when we have a pure moving average model, and we look at the sample autocorrelation, then it becomes 0 when the lag is greater than the order of the model. If we do the sample partial correlation matrix function of an autoregressive process of order p, then it becomes 0 when you evaluate it for orders greater than p. So it's exactly the same thing as in the univariate case. It's just that each time, instead of getting one plot, then you get, you can say, the dimension square plots. If you, I won't cover the so-called Q-condition partial correlation matrix function because we won't need it. We will kind of restrict ourselves to what we've done previously and stay there. I think that's the most appropriate thing. Now, what we did last time was to do pre-widening. When we look at models in a multivariate sense, we don't do it the exact same way to identify a model. So one thing, what can be done, is that you take for each of the series, in this case xt and yt, and then you fit individual univariate models to those. That you can do. It's just work. Then you take the residuals from those models, so you don't filter the other signals with the models you estimated for one, but you just look at the residuals from each of the models. And then you compare with the plus minus 2 over square root n for the cross correlation, and then you see what happens. So, as kind of said, it's not the same as what we did last week, because we do not filter the other series with the model we estimated for the input. That's a very important difference. Now, in case you have a multivariate model like this, if you do this up here, you will end up making a model where you have, or at least it's equivalent to the following model. You calculate the determinant of the phi operator here. We have one model over there. The determinant contains products of the impulse responses or transfer functions. So generally the order will be higher. You make that a diagonal matrix with all those polynomials in there. So the order is higher, you have more coefficients. And then you take the adjugate of your moving average part, adjugate of your phi, and you multiply that on the moving average part. Those are the models that you're likely to estimate when you identify the individual models. Because you do things, what you try to do is exactly to make something on the diagonal and try to compensate for everything by doing that. So that means that what you will end up having is a model with a much higher order than if you could estimate in the original model. So in practice, even though it's described, don't do this. Because you'll just end up finding things that are too complicated. We'll get back to next week how to just estimate models and do things pretty much the same way as we've been doing from the univariate models. So what to do? Well, for the general representation or the coefficient representation here, in general, when you have this multivariate ARMA model, there's no general analytical solution, only in the case where for the pure autoregressive model, there is an analytical solution. We did it the same thing for the univariate models, that you can do a least squares estimation. But in general, what you need to do is you need to look at algorithms, as in numerical optimization, in order to find estimates. Now, if you have complex models, high-dimensional models, you have many coefficients to estimate. All of a sudden, the numerical challenges in doing that are not so easy. So basically, as said, if you have an autoregressive model, multivariate, also including exogenous input, then you can just do least squares. So that is nice. We won't spend too much time on that. If you have the multivariate ARMA model or RMAX model with order P and Q, then there are basically two options. One of you also saw the challenge here. Sometimes when you do just the condition sum of square in the ARIMA model, it will give you an estimate that is not stationary. Thereby, you cannot use maximum likelihood afterwards. Then you need to start with maximum likelihood all the way through. Now, the split method, which we'll discuss next week, is basically a conditional sum of squares model. But what we said for the ARMA model is that we can only do that so far if it's a pure AR model. But what is in the split model is how to get an approximation of this for an ARMA model as well. This is, to some extent, along the lines of what ARIMA does when it does a conditional sum of squares for the moving average model as well. Or we can do full maximum likelihood, which of course, I think I said it many times, I prefer that, but sometimes it's just taking too long time. So what we will discuss next week is, well, I will share a paper by Henrik Splid, where you can see what how his algorithm is working. It probably contains some linear algebra that you haven't used too much, at least for most of you. So what I want you to do is to kind of look at it. Don't necessarily expect to understand everything. And I'm looking at particular individuals to say, don't read it too carefully, but read it to get an idea of what is going on. And likelihood, well, we know how that works. It's basically the same thing as what we did for the univariate models that we can do in a multivariate setting. Then it's just a multivariate normal distribution that we will assume at every time point. And we just go through it. The only problem is the number of parameters that we have to estimate. If you have a bivariate ARMA 2, 3 model, how many parameters should we estimate? Oh, that's maybe too much calculation for right now. Sorry? Nope. Much more. You said 14? How do you get? I don't know. 10 I could guess, but I cannot guess where 14 comes from. Let's demystify. Each time you have a coefficient here, how many parameters does an AR1, a bivariate AR1 model have? Let's start with that one. You have a matrix here, right? It's a 2 by 2 matrix. So you have 4 coefficients there. But then you skipped something. What you typically, well, again, it depends on the, so you can say in this case, you have 5 2 by 2 matrices. So the number of parameters in that model is 20. Whereas in the univariate case, it's just 5. But then there's one more element to it that we say, well, we don't estimate, we just derive it from our estimates. When we're in the univariate case, we have a sigma that we just estimate. In the multivariate case, we have a 2 by 2 covariance matrix. So we also there have how many parameters do we need to estimate in a covariance matrix for a bivariate noise. How many parameters are there in that? 3. Thank you for not saying 4. Everyone agrees why there's 3 and not 4? Anyone? Yes? So, to be a covariance matrix, what you have is the variance with yourself for the first state and for the second state. But then it's the off. Now I use the wrong notation. I should like that. I should write sigma 1, 2 and sigma 2, 1. Now this matrix has to be symmetric. So this one has to be equal to sigma 1, 2. So due to symmetry, thereby it's only 3. But then go to a 3-dimensional system. Assume this was a 3-dimensional system, then it's 5 coefficients each with 9 elements, right? So then you have 45 parameters for the same model as such, same model order. So all of a sudden, the numerical optimization problem becomes a bit more challenging. I don't know how many of you have done optimization where you have to optimize more than, say, 20 parameters. How many of you have done that? I mean, I have, but I guess you've all done things with 5, right? Maybe not even. Through numerical optimization, whenever you get to a high-dimensional space, it's very difficult to predict what actually happens. There may be a lot of local minimas and other things. It's not the content of this course, but that's the reason for that. That is actually the motivation why ARIMA does the conditional sum of squares to get a solution that is near the optimal point for the maximum likelihood estimate, to start there and then try to navigate from there. So what have we looked at today? We've looked at a closed loop. I don't think I actually used that word, but it's kind of obvious to see that where that comes from. You have a feedback loop here, so it's a closed loop. It's a word that you often use in control theory, whether you have open loop or closed loop control. Now, we looked at multivariate ARMA models, stationarity and invertibility, and a model of other things are just fairly obvious extensions of the univariate settings. It is to a large degree the same thing that we just do. The one thing to keep in mind is that where in the univariate case, the autocovariance to lag k is equal to the same lag k minus 1, but we see that when we do it multivariate, we need to transpose as well. I think that's the one thing to just keep in mind when you do calculation with this. And then I like the fact that you can take any model and write it as a vector autoregressive model of order 1. Sorry, any vector ARMA model, not any model in the world. We have to restrain ourselves a little bit. I like that fact because then it means we can put everything on the same shelf. Also because when you're running, say, a real-type system, at least in programming it, it's very convenient to not have to keep track of what happens 10 time steps ago. You only have to keep track of the most recent state in order to predict the next state. So even though you effectively have dependence 2 steps backwards in time here, then you can make an implementation that only has dependence 1 step backward in time, no matter what the model structure is. I think that, for me, that's a very nice structure. There's one odd thing, that's the covariance structure out here. Because epsilon t here is univariate. It's not multivariate. So if you consider this a multivariate model, you have to add 3 fake noise signals and 2 fake noise signals and 2 columns of zeros. Then you have 0 covariance in the diagonal there, which can kind of lead to things, at least you don't want to invert that matrix. But so it is a little bit odd relative to a full-blown vector autoregressive model, but it gives you a way to represent things in a way where everything is just depending on the previous point in time. I think that's at least that's a part of this that I use. I wouldn't say all the time, but quite often. Any questions? Yes. So when we look at the closed loop here, these could be ARMA models themselves. Indeed. I did not do that. And if I wanted to do that, basically what you have to do is to, instead of having this here, let me take a different color. And write it down here. You could have, say, are they correlated or independent again? Last week we assumed that they were independent. So what we could have would be a transfer function from n to y here of b, and then a 0 and a 0 because they are independent. And then the transfer function from n2 to x down there of b, and then an epsilon t and eta t here as white noise input. Then you could have ARMA models down here as well. I just didn't want to go through the full rigorously definition. And I think also in the slide, here, I did exactly that. It's the only difference between there and here is that compared to the previous slide, in the example here, I multiplied everything that is a denominator true to get a non-fractional system. But that is indeed what we could do. That was why I wrote n over there to say it's just noise without specifying the color of that noise. But it could have some color specified by those extra transfer functions there. Other questions?